Greetings of the day. I'm Shravani Kurma. I'm pursuing a Ph.D. in the Institute of Communications Engineering Department, working under the guidance of Dr. Keshav Singh, National Sun Yat-sen University, Taiwan. I'm grateful to be a part of MILCOM Conference 2022. Today, I would like to present to you our work on outage probability analysis of uplink self-read massive MIMO with user mobility. The co-authors of this paper are Professor Prabhat Kumar Sharma, Professor Chi Ping Lee. Here are the contents of this presentation. Introduction to the self-read massive MIMO in 5G and beyond 5G. The fifth generation wireless communication systems have witnessed continuous progress in terms of the brilliant technologies such as network function virtualization, millimeter wave communications, reconfigurable intelligent surfaces, and full duplex relaying, etc. One of the pivotal technologies which is widely discussed in 5G communication systems is multiple input, multiple output system, in short, MIMO systems. Let us discuss a bit about the key features of MIMO systems. Firstly, MIMO systems provide macroscopic diversity. Secondly, large coverage probability. Due to its macroscopic diversity nature, MIMO systems can provide service over a larger geographical area. Thirdly, high spectral efficiency. Spectral efficiency is also called bandwidth efficiency, and it refers to the rate at which the information can be transmitted over a given bandwidth. The fourth one is spatial multiplexing. Spatial multiplexing in wireless communication is based on multiple input and multiple output technology, where multiple antennas at both the transmitter and receivers carry the multiple data streams simultaneously with the same frequency band. In self-read massive MIMO systems, the number of access points is fairly large. The approximate density is like 1000 per square kilometer. Here, when we consider multi-user MIMO technology, multi-user diversity is an advantage, but there exists inter-cell interference. In order to overcome these difficulties, we'll go for self-read massive MIMO technology, which is a combination of distributed system and massive MIMO. In self-read massive MIMO, there exists no cell boundaries, and all the access points are distributed in the considered geographical area and are connected to the central processing unit to jointly serve the user equipments. Here are the advantages of self-read massive MIMO. Firstly, it avoids excessive inter-cell handovers, or there won't be any inter-cell interference, and it diminishes the detrimental shadowing effect, and it controls the signaling interference. It has the ability to offer similar quality of service to all the user equipments despite its low complexity signal processing. Here is a brief motivation to the paper. Adopting the practical scenarios such as user mobility and imperfect CSI, there are papers like 18 to 21. The works in 22 to 25 have assumed the availability of perfect CSI at communicating nodes, which is making the system comparatively less practical. Moreover, previous works have investigated these aspects for cell-centric systems. Further, the mathematical framework of the self-read massive MIMO, especially considering all the practical scenarios like user mobility and imperfect CSI, which is becoming significantly critical in upcoming wireless communication technologies, and that is missing. Moreover, mobility-aware spectral efficiency is analyzed in 17. However, they haven't discussed about analysis of outage probability. Motivated by all the above discussion, in this work we are going to consider self-read massive MIMO multi-user network, considering all the practical scenarios like user mobility and imperfect CSI. Coming to the contributions of this paper, in contrast to 8 to 12, we studied the cumulative effect of the practical scenarios like imperfect CSI and user mobility on the system's outage performance. Moreover, user mobility is investigated under various Doppler power spectrum models. We utilize Welch-Scatterworth approximation to derive the closed form expression for outage probability. And this approximation handles the summation of gamma random variables perfectly. We also demonstrate the impact of mobility on the outage probability for the increased number of users and number of access points. Moreover, the impact of the imperfect CSI for increased M and target threshold SINR is also demonstrated. Here we go with the system model for the self-read massive MIMO network consisting of a CPU, geographically distributed M access points, and arbitrarily distributed K single antenna user equipments, as we can see it in the figure 1. Each AP is equipped with N antennas and it is connected to the CPU. The channel gain between the kth UE and the nth antenna of the mth AP is given by the equation. As you could see, the GMNK is equal to phi MNK power 1 by 2 HMNK, where phi MNK is nothing but a large scale fading coefficient and HMNK is a small scale fading coefficient between the kth UE and nth antenna of the mth AP. Coming to the signal model, the large scale fading coefficient var phi MNK is nothing but the product of path loss and log normal shadowing correlation factor. We consider three slope path loss model, as we could see here, where DMNK is the horizontal distance between the user and AP, and D0 and D1 are the reference distances. HMNK is nothing but independent but not identically distributed, which is like a complex Gaussian fading distribution which has Rayleigh envelope with a scale parameter called sigma. According to Jake's model, the time adjacent channel gains of the fading lengths HMNK are considered to be uncorrelated with the correlation parameter rho MNK. The correlation parameter rho MNK depends on the type of scattering model, and it is given in a tabular column which we will be seeing now. Here we can see the Doppler power spectrum models along with their correlation coefficient. For now we have rectangular, Gaussian, uniform, first order Butterworth. Coming to the time selective fading. Due to the time selective fading, using a pilot signal, we estimate the channel coefficient HMNK over the first signaling point of each transmitter block, and the estimated version is represented by H hat MNK. And as it is the first signaling, we use 1. Thus, we expand HMNK for the ith signaling position in terms of the first signaling position like this. HMNK of I is equal to rho MNK power I minus 1. HMNK at the first part plus H epsilon MNK of 1 plus phi MNK, which H epsilon, this represents the error part. So from 1 and 3 we get GMNK, where the GMNK is nothing but var phi power 1 by 2 into HMNK, but as we are representing it as first signaling point, so the third equation will be substituted in the first equation and we'll get GMNK I, which you could see in the equation 4, where phi MNK is defined as 1 minus rho square with the summation part of rho MNK power I minus L minus 1 EMNK of L. And H hat is nothing but the estimated channel coefficient, and H epsilon MNK is nothing but the estimated error. EMNK of L is assumed to be distributed as complex Gaussian with the zero mean and sigma square as its variance. Coming to the performance analysis, the uplink received signal at the mth AP is given by Ym, which is equal to summation of n is equal to 1 to capital N, because we are considering for each and every antenna, so we are considering n is equal to 1 to n. K is equal to 1 to capital K, which is nothing but at every user, and GMNK of I under root of PK XK plus N. PK represents the power, uplink power transmission of the kth UE, and XK is nothing but the transmitted symbol of the kth UE, and N is nothing but the additive white Gaussian noise at the nth antenna, hence it is represented as NN. From equation 5 we can see that GMNK has been expanded in terms of HMNK. From equation 5, the effective noise variance at the mth AP node is computed as sigma square, which is given by the equation as you could see in the equation 6. The signal to interference plus noise ratio, which is nothing but SINR of the kth uplink UE at the mth AP, is given by sigma MK, which is equal to, as you could see in the numerator, we have the part which is there at the kth UE, and in the denominator you can see U is equal to 1 to K. That means where U is not equal to K. So the first desired signal at the kth is given on the top, that means on the numerator, and in the denominator we can see that U is equal to 1 to K, where U is not equal to K. That means all the interference other than the signal which is at that particular K, and along with the noise, which is nothing but sigma square. By putting XMNK, which is equal to CMNK multiplied with HMNK of I square, where CMNK is nothing but the simplified version of this var phi and rho term, and we get the simplified version In the numerator, summation of n is equal to 1 to n xmnk, and in the denominator, summation of n is equal to 1 to n and summation of u is equal to 1 to capital K, where u is not equal to k. That means all the interference terms, that is xmnu plus sigma square as a noise. We knew that hmnk, the estimated hmnk, which is nothing but Rayleigh distributed, which is given as sigma hmnk divided by under root 2, where hmnk square can be denoted by Rayleigh square, which is denoted by gamma distributed, and the gamma with mean value 1 and variance are sigma square. And when we consider the CMNK multiplied with HMNK square, which is nothing but the scaling of gamma, which is nothing but due to the properties of the gamma, we can take the scaling parameter inside the variance. Like gamma of mean 1 and variance is equal to CMNK and sigma square. So in order to evaluate the outage probability expression, we consider x and y as the random variables, which are defined as x is equal to summation of n is equal to 1 to n xmnk, and y is equal to summation of n is equal to 1 to n and summation of u is equal to 1 and to k, where u is not equal to k xmnu. So in order to evaluate this summation sum of independent gamma random variables with different shape and rate parameters, we use wedge Scatterworth approximation. Let z is equal to summation of I gamma random variables with psi I and theta I as its mean and variances. Then the mean and variance of the z is given by E of z, that means expectation of z is given as summation of I terms of psi I, theta I, and the variance is given as summation of psi I and theta I square. Using wedge Scatterworth approximation, the means and variances of x and y are computed and has been given in 14, 15, 16, 17. So let us consider kx is equal to square of the expectation of x divided by variance of x. Ky is equal to square of the expectation of y divided by square variance of y. And theta x is nothing but variance divided by expectation of the x. And theta y represents the variance and expectation of the y. We know that x is nothing but gamma of kx theta x, and y is nothing but gamma of ky and theta y. Thus, the cumulative distribution function and probability distribution function of x are given by 18th and 19th equation, where it is nothing but gamma distribution function. Similarly, the CDF and PDF of the y are given respectively by 20 and 21. Now, sigma mk in 8th equation can be simplified as c is equal to x divided by y plus sigma square. Note that for larger values of m and k's, y is far greater than sigma square, and thus we can say that c is equal to x by y. The CDF expression of c is given as probability of c less than or equal to c, which is equal to probability of x by y less than or equal to c, which is given as integration from 0 to infinity fx of cy and f of y dy. After substituting fx and fy, which we have derived earlier, we get the simplified expression for cumulative distribution function, which is nothing but I divided by sigma kx, sigma ky, theta y power ky, where I represents the integration from 0 to infinity gamma kx cy divided by theta x, y power ky minus 1 e power minus y divided by theta y dy. As I is in terms of the integration, we can evaluate this I part by considering Gauss hypergeometric function. And finally, we could able to get FC, which you could see in the 26th equation. So, by using 27, we derived 26, and the outage probability of the kth UE at the mth axis point is given by P out m at k is equal to FC gamma th, where gamma th is nothing but the considered threshold, which is nothing but probability of c less than threshold. The final expression is denoted by 29. Using 29, the total outage probability of the kth UE is given by the outage probability at k is because of all the access points, right? So we have to consider the access point 1, 2, 3, 4 up to n. So it is a product of the outage probabilities considered at each and every access point, which is cumulatively gives the total outage probability of the kth UE. And here we go with the simulation parameters. Here the figure shows the outage probability of the self-free massive MIMO system versus number of access points, which is denoted by M, under perfect CSI and imperfect CSI scenarios. In general, to evaluate the system performance using imperfect CSI, we use channel estimation error. Here we consider the channel estimation error for nth antenna of the mth access point to the kth user channel. It is observed that the outage probability degrades significantly for imperfect CSI with 20% channel estimation error when compared to the perfect CSI, which is like 0% channel estimation error. Furthermore, we can also observe that as the number of access points, that is M, increases, the performance degradation of the system decreases. That means the system performs better when M increases. Here we can notice that the impact of channel estimation error is almost negligible for lower values of M, and it is quite noticeable for larger values of M. Furthermore, as the number of users, that means K, increases, the outage probability of the imperfect CSI becomes very close to that of perfect CSI case. This figure shows the outage performance of the considered system for various Doppler power spectral models. We have set the mobility to 20 miles per hour for all the Doppler power spectral models here. While comparing the mobile users for various power spectral models, the rectangular power spectrum model gives the best outage performance, as we could see in the figure. Moreover, the worst case of the outage probability is observed using Gaussian power spectrum model. And the first order Butterworth and uniform power spectrum models have almost similar outage performance, and its performance lies in between the best and worst cases of the Doppler power spectrum models. This figure depicts the impact of user mobility with the rectangular Doppler power spectrum model for the considered self-free massive MIMO system. It is observed that the system's outage performance is significantly deteriorated by the user mobility. This is because of time selective nature of the channel. And when multiple users with low mobility or no mobility are considered, there is a significant improvement in the outage performance compared to the high mobile users. Moreover, the impact of mobility is quite less when the number of users is more. For instance, when K is equal to 60, the difference in mobility case and the no mobility case is quite low as compared to that of K is equal to 20. Here, the outage probability of the considered self-free massive MIMO system is evaluated for various M with the K is equal to 20 as shown in the figure. It is observed that there exists a significant drop in the outage probability as M increases. This is because of spatial diversity. That is, the distributed access points provide better SINR to all the users. Moreover, the perfect CSI yields better outage performance. As we could see, for the increased target SINR threshold, the outage performance degrades significantly for imperfect CSI of 20% channel estimation error when compared to the perfect case, which is like 0% channel estimation error. Coming to the conclusion of this paper investigated the outage probability of the self-free massive MIMO system with various Doppler power spectrum models considering perfect and imperfect CSI scenarios. The simulation results revealed that the considered system improves the outage performance as the number of access points increases. The results of the outage probability with perfect CSI is better than that of imperfect CSI. It is also concluded that the user mobility due to the time selective nature of the channel affects the system's outage performance. Moreover, the rectangular Doppler power spectrum density is chosen to be the best one for the system considered, and it provides a better outage performance compared to that of uniform Gaussian and first order Butterworth spectrum models. So coming to the future plan, the main challenge for the large scale self-free massive MIMO is the computational complexity. Generally, the computational complexity for the signal processing, resource allocation, and front haul requirements grows polynomially with the increase in the number of access points and the user equipments. In our further research, we would like to consider the outage probability analysis considering limited capacity front haul links and full duplex self-free massive MIMO. And these are the references which we have used in our paper during our analysis of the considered system model. And thank you.